All right, everyone, welcome back from the exam number two. Um, Happy to report that the average on the exam was a 93.4%, which is actually comfortably in the A range for the exam, so perhaps even a little bit better than I expected based upon the previous classes. So the good news is that everyone's doing quite well. I calculated out for everyone. I think it's still possible for everybody in the course to still get an A, and I couldn't be more happy about that. So, just as I mentioned for the first exam, I would expect if you did well and you handle this material well for this exam, you'll do perfectly fine on the remaining exams. This sort of marks a little bit beyond halfway in the problem sets and halfway in the exams. So everyone has a pretty good handle of what's going on by now, I hope. Everyone's doing really well, and I have nothing to say about that other than just keep it up. So obviously your grades are posted. Um, uh, Everything's on the online, and you can see how you're doing. But please keep going with the weekly problem sets as we talked about, and prepare for more sort of the same for exam number three. In several weeks. So again, really great turnout on the exam. Regarding the worksheet, I gave everybody who did it before I decided to extend it perfect 10 points. But basically, I had enough complaints about not having a problem sheet and an exam on the same day that I made the problem sheet move back to the end of this week. The second reason for that is that there was overlap in this problem set between lectures material that was going to be on the first exam and not, and I didn't want to confuse anyone. Hopefully, it didn't cause any problems, or hopefully the move just provides some extra time to relieve stress, not create it. Always my intention, but I know it can go both ways and things change. But at any rate, next worksheet is due later this week. So without any more to do, I'm going to move on to continuing the lecture about rivers and flooding. So if you remember, before the exam, we had one lecture on rivers and flooding. Dealt a lot the hydrologic cycle, again driven by the sun, that drives precipitation, evaporation, and infiltration to surface and groundwater. And where we're going to spend, again, most of this week is talking about the surface waters, rivers, and particularly, river-related hazards and plans to mitigate hazards and things like climate change. So where we're going to pick up today is actually talking about the discharge. This is the amount of water moving by a particular location in a river per unit of time. So basically, you can look at, go down to Columbus, you can look at the Olentangy River coming through, and you can measure the discharge in an area, and that's the volume of water moving past that location per unit time, and that's usually done in orders of units of cubic meters per second, or CMS. There's a particular equation for this, and it's Q, which equals the flux, equals the width times the depth times the velocity. And if you can imagine how wide the river is, how deep the river is, and how fast it's moving, is basically a volumetric unit of just how much water is moving past period of time. Some people write this as the Q, or the flux, equals the velocity times the surface area of a column of water coming past a given location. But the key things here to remember are that Q is the discharge, again, typically measured in cubic meters per second. W is the width of the flow of the river of the channel in a particular area. D is the depth of that flow in an area, and V is the velocity, or the meters per second that water is traveling. So for those of you who come from a civil engineering background or taking courses in civil engineering, they particularly, in earth science, we typically call it the discharge equation. Engineers tend to call it the continuity equation. Today, those terms are used interchangeably between the fields. So a key thing to remember here in terms of predicting hazards related to the rivers is that if you have a wide, shallow, deep channel, for example, okay, and you have fixed velocity of that water, that fixed flux going past a unit area. If you move into an area where the river narrows or shallows, that's going to cause the velocity to increase rapidly. So it's a sort of a conservation of mass problem, where the area and the velocity, the Q remains constant at any area down the river, as long as the water is not lost by infiltration into the groundwater, evaporation. And as a result, if you have a narrowing channel or shallowing channel, the velocity will actually increase. This is what locally creates things like rapids in the Rocky Mountains, or in sort of Rocky Mountain streams, for example. So basically, This is similar to the same concept of Bernoulli's principle, how planes stay in the air, which is that you have to have a fixed conservation of mass on both sides of the plane wing, causing lift of the plane. Same thing in rapids, where the velocity will increase because of the fact that a fixed mass of water has to move past a particular point in time. So obviously this means the flux, again, if water is not lost or gained, will remain constant, but the velocity can change depending on how big the channel is. The channel's wider and deeper, things will slow down. That's not going to be a rapid. If the channel narrows or becomes narrow, the water will increase. And if you think about this, if you've seen pictures or videos of your friends or yourself going down rapids, you always see the rapids are both fast moving, but you also see rocks and other hazards there. So implicitly, it's showing the channel is getting shallower and many times getting less wide. So I won't ask you to calculate anything in this class particularly, but you should definitely remember that discharge is the volume of water moving past a particular location for a period of time. And I would remember this equation. I won't ask you to manipulate it mathematically on the third exam, but I'll certainly ask you to reference it. So what we're going to talk about a little bit is sort of how we as humans have manipulated that that discharge equation. Particularly, we're going to talk a little bit about how building and removing dams can influence that discharge and actually influence ecosystems, as well as how natural systems, different variations in river channels actually influence likelihoods that lead to flooding and things like that. So here's an example of a pretty standard example of a dam. And the key thing here is this would normally be a river channel, change in topography, so as the water's flowing down the river channel. But in this instance, we put a dam in the middle of this river. And importantly, this is true pretty much of all dams. This actually causes a few things to happen. All the water behind the dam, of course, will start to slow down, right? Because we're going to change the difference in that grade. We're not going to let the water out. So the water is going to eventually slow down. The water will deepen near the area of the dam, often creating a reservoir or a lake. But that actually has some pretty important implications to the discharge equation. And particularly going back to what we talked about a few times in the last few weeks is related to sediment deposition. So as a result, often the area before you get to the lake or reservoir, you see major episodes of sediment deposition. If a river has a large flux of sediments, this can lead to incredible volumes of sediments being deposited. Oftentimes these can lead to shallowing of river channels, and often these have to be dredged or cleaned out to make sure that doesn't occur. And the other aspect of this is that beyond the dam, wherever that water that eventually comes out over the dam, it can be through the dam by hydroelectric channels, it can be a spillover, it can be often just chutes around the dam. You often increase the amount of energy that's going to be there, and you cause erosion. So that can cause major changes in land profiles, sediment deposition, and quite frankly, ecosystems in the areas near the dam. So, today in the United States and most of the Western world, and Europe, North America, Canada, Australia, it's quite popular to think about removing dams. People have long since used these dams for hydroelectric power, but now there's a bevy of concerns related to the ecological damage, the controls of sediment deposition. We talked about this, for example, in New Orleans, where the sediments being starved from the coastline have led to major implications from hurricanes and typhoons, can cause changes in ecosystems, not allowing fish to come up to spawn, all these different things. So in some cases now, particularly in the United States, Western world, we are actively removing dams in many instances. So this is an example of an area from northwestern United States, in Washington State, where the dam's being removed, and there's a major flux of sediments where that mass of sediments have accumulated now, basically both being wiped out of the river channel, but also the natural process of sediment deposition to the river channel are being restored. So let's just think about this for a second. How would removing a dam, impact habitats? How would it change sediment accumulation, lead to changes in nutrient fluxes? Obviously, this is a pretty major change in the ecosystem, both when we put it in and now when we take it out, right? So in both cases, there's concerns we need to consider. Obviously, the effects of dam removal immediately can have pretty profound aspects related to sediment deposition, related changes in the river channel. If you go back here, removing a dam obviously is going to probably remove a lake or a reservoir where water's accumulated, and probably ecosystems that developed around that. and eventually places that are been washed out by erosion are going to have their profile change as well. So they can be pretty profound. So again, this is an example in the state of Washington, where there's removal of dams in the Elwha River, and this has led to major flushing of sediments that have accumulated in the river channel behind the dam into the Strait of the Juan de Fuca, for years. And this process is expected to last 5 years, where this massive amount of sediments are being transported out. Locally, it's great for nutrient flux at the time. It also changes some amount of the phytoplankton activity in the area, obviously, but there are a lot of people who are concerned about the look, the quality of water, changing river channels, and difficulty in doing sort of river transport along, transportation along the river on boats because of these things. So coastal impacts. Obviously, one is just thinking about changes in phytoplankton activity. Another to consider here is the fact that you're going to see a progradation of the delta out into the coast. From the coast outward, you probably will see a revival of beaches in the area, which will no longer be sediment starved, as well as possibly the formation of deltas that'll progress out into the ocean. And in that area, that latitude, typhoons aren't necessarily a huge concern, but certainly there'd be greater protection from things like that, as well as tsunamis, for example, by having more of an established coastline. So just for perspective, this Elwha River dam removal project actually extends back quite a ways. There's the first one is moving the dam at the Elwha Dam at Lake Aldwell. So this is a lake, you can see in the orange, was a lake that formed after the dam was formed. Obviously, the removal of that dam is eliminated that lake and changed the ecosystem in that area. Similar at the Glines Canyon Dam and Lake Mills further up the river. This has now been removed in 2014. And in both cases, you still see a prolonged, almost a decade with the removal of these two dams, of major sediment fluxes out into the Strait of Juan de Fuca in the area. So this is at the Elwha Dam, Lake Aldwell. This is the before shot. You can see major. This is the rivers flowing downstream in this direction. You can see the dam is here. Major hydroelectric power plant, a lake. It's used for tourism, as well as fisheries and things like, there is fishing, stuff like that there. But that's the before shot. You can see after shot, after the dam is removed, basically right in this area. You can see that now the river channel is a very different beast than it was before 2011. You'll see here, obviously, at different times of year may vary, but you see what we'll talk about in a few minutes is a braided river system that sort of flows down through here. Here's some narrowing of the channels. As we talked about that flux equation, you can see there's rapids forming in this area where the channel is narrowed, as paired up here where it was probably wider, and the discharge equation didn't have that increase in velocity. So obviously, you can think about this. I won't stop answering questions, but this is going to change the fisheries in the area. This is going to change potential to actually see boats or kayaks or whatever they might be sort of use this water area. That matters on the human side, but this has major implications for example, things like climate change and greenhouse gas emissions, for ecosystems around this area, which have been basically sub-lacustrine or below water for a long time, that are now going to basically be part of the sort of forest system in the area. So I apologize for this being sideways. I forgot to change this, but basically all I'll say, I'm not asking you to read this sideways, and I'll change this on the slides, is that similar concerns or similar processes are actually ongoing in Columbus themselves. So in the state of Ohio, when I got to Ohio State, there was an existing channel on the Olentangy. It was a wide channel. The goal here is to actually narrow and deepen the channel to kind of keep a continuity of flux, but actually create more of a riparian system. So other aspects of what the hope is by moving these is you can actually store more carbon in vegetation and biomass in the river channel, and that can actually help mitigate some aspects of climate change. There's a lot of carbon. There's a big carbon source in the rivers that are often lost to the atmosphere. And one idea is that by deepening the channels, narrowing and creating sort of more complex channels that have vegetation, you can store more biomass on the continents in these land masses. And if you take a walk over, behind the football stadium over to West Campus. If you've driven across that bridge, you can look down and you can see a little snippet of an area where they actually have changed the river channel quite profoundly. And this is not unique to Ohio State or anything like that. These are part of dam removal restoration projects all over the country that are designed to sort of a rethinking from our perspective on how important these dams were for flood control versus how we can mitigate floods by putting more water and sediment and carbon in the river channel and storing it there permanently. So this is the image I'd prefer you look at. Apologize for that being sideways. This is what things looked like back in about 2012, a wide, relatively shallow channel. There's going to be an attempt here to deepen the channel a bit. That'll narrow it a lot. That might make water move through that area faster, but there's also going to be a sort of a manufactured braided channel that's going to put a lot of the water through this proposed now actually developed wetland, creating an ecosystem for wetlands of still riverine, but where you're going to store biomass, attract fish, and kayakers and all the like. So again, by deepening the channel here, creating this system, they can put a lot of water through there, store carbon, and sort of do flood control in other ways besides just the long-term history of deepening, widening and deepening channels to control that discharge and putting in dams, which is what we've basically done for about 150 years or longer in the United States. Other parts of Ohio where this is pretty prevalent, this is on the Cuyahoga River. In the last decade or so, there have been 2 dams recently removed along the Cuyahoga River near the town of Cuyahoga Falls. Main issues there is that the water that was getting stagnant was leading to algal blooms and a strong smell. The removal of the dam, those sediments that are building up behind the dam sort of feed that microbial and phytoplankton development, and removal actually help allow the water to flow and minimize the sort of buildup of nutrients, sediments, and stench in the area. There are different recreational opportunities now in terms of fishing and stuff like that. And the nice thing, and this is important long-term impact of dam removal in general, is increased biodiversity locally. You start to see more of the sort of natural fish moving through the stream. That brings birds of prey. You see things like bald eagles were definitely endangered for a lot of reasons, mainly pesticides and hunting and things like that, but also actually having the flowing streams be more prevalent where these natural fish and whatnot can migrate through. There now is actually opportunities for the birds of prey, and you're seeing those, particularly the bald eagles coming in the area, and then it may not be popular, but natural bugs and stuff like that coming back rather than things that are used to living in lakes and stuff like that. So I'm covering that relatively quickly, but suffice it to say, the removal of dams, particularly in the Western world, could have major implications. They've been a major component of renewable energy for a long time in the United States, particularly along the coastlines, Pacific Northwest and Northeast, and especially. But the long-term concern is like while they were built for electric and for flood control, now with a revitalized way of thinking about this discharge equation and thinking about issues related to climate change and ecosystem removal and stuff like that, people have tended towards removing dams in North America. The idea to return things to natural systems, let the natural fish species and bird species sort of go back to the static norm, and the idea of managing the channel to store more carbon to slow the rate of water by creating that side channel. Unfortunately, or from at least from some perspectives, as some dams go down, others go up. So I'm a little bit. I said unfortunately, that's probably placing a value statement. I apologize for that, but largely, I think there's concern that people around developing countries in the world are going to sort of go through the same process. Put dams up for 50 years, distort ecosystems for some purposes, controlling floods or getting hydroelectric power, and eventually they're going to recognize they might be problematic. But I apologize for putting a value statement on that. It wasn't my intent when I started speaking, but it just slipped out. But this is particularly common phenomena particularly in rural parts of China and in Africa, where the need for hydroelectric power, the idea of water poverty, so there's not enough water for agriculture and drinking, and energy poverty, where there's not enough. They don't want to switch to fossil fuels, burn coal or natural gas or oil. So it creates opportunity to have hydroelectric power and make power that can be used for their meet their electricity needs. People putting dams in. So this is one of the more famous dams built, I guess, finished in this century. This is the Three Gorges Dam in China. Cost $26 billion US to build a dam, and it's a major source of hydroelectric power. So, what's the rationale for why we put dams in the first place, and why these, many countries are putting them in now? Their budget on greenhouse gases actually shows a positive trend. So, in the right locations where you have to bring on major sources of fossil fuels to meet power needs, it can be beneficial to do hydroelectric power. So on the balance, this dam is designed to reduce gas emissions when it's running at full power, because there would have been about 31 million tons of coal needed per year to handle the growing populations and power needs in that electricity needs in that region. So this basically allows this dam to be used for hydroelectric power, not lead to the development of new coal-fired power plant consumption, and that has an offset of about 100 million tons of greenhouse gas emissions per year. So obviously, this has other effects there. They don't need to mine coal and other things like that. In this perspective, on these really large dams, it's really important because it actually generates about 1.7%, which doesn't sound like a big number, but when you think about the energy needs of a country of more than 1 billion people that has a rapidly developing economy, this is nearly 2% of the total electricity demand for the entire country as of 2011. That's a pretty big amount of energy that's generated. The other issue really here is that there have been a history of major flooding events that did a lot of damage, and these are some reasons that we developed the dams in the U.S. and in other parts of the world. So it's not an unfamiliar rationale, but this has led to reducing flooding in downstream areas from about once every 10 years to about once every 100 years. So they're able to minimize the amount of flooding by having some regulation of the water in this area. If you were familiar with Ohio's history, the Conservation Corps, or the Civil Corps, or the Army Corps of Engineers, this is pretty similar. The Cuyahoga River Dam I mentioned to you, I forgot to say this, but there used to be flooding events there every 5 to 10 years, and they were stretched out quite a lot by having a dam that kind of controlled that. Of course, now, as I mentioned, we're using intentionally braided river channels and wetlands to sort of mitigate that, not just dams. So the last aspect, and I think this is a really big one, is this actually increased the shipping capacity. A big part of the problem along the Yangtze River here near the Three Gorges Dam area was that the dam can now actually use the dam that's built up there to mitigate dryness in the Yangtze River during the dry season, so it can increase flow rates and actually keep transportation of cargo and shipping available. So everybody has to make value decisions based on economic and ecosystem considerations. Clearly, there's a move to remove these. Punchlines, there's clearly a move to remove dams based on some concerns, and develop sort of smarter ecosystems around river channels. In other cases where there's rapidly growing economies and rapidly growing populations, just like we had earlier parts of the last century, there's a lot of dams going up for hydroelectric power, shipping, and power generation. So, looking at this Three Gorges Dam in more detail, what are the problems and concerns associated with this? Well, in a country with 1 billion people, this is the before picture in 1987. This is after completion in 2006, and you can see, the Yangtze looks a bit wider up here, obviously, but notice that the amount of water that's ponded up back in these sort of tributaries to the Yangtze, and then also notice how big the dam has become near the area, or how big the reservoir has become near the area where the dam has been built across this area here. So much greater amount of water stored there. Obviously, the water flowing over the land surface and becoming lakes on these tributaries has the net result of actually displacing a lot of people. So at the time it was built, it was estimated about 1.3 million people living in these low-lying areas along river and creek tributary shorelines are now now underwater, and of course they were displaced and had to move to other locations. That's the a very common phenomenon in the United States where we've built dams as well. Um, One of the things that's been brought up uh, in this area is, of course, led to flooding of valuable archaeological and cultural sites. Many times, burial grounds, things like that, are covered up by these things. Um, and just like that dam photo or cartoon I showed you earlier, where the downstream of the dam or down here there can be major erosion. This erosion is now there's some concern that's impacting Shanghai, and they're trying to manage a way to control erosion. Control sediment deposition above the dam and erosion below the dam, and that's a problem that people have been chasing for a long time. So for perspective, 40 million tons of sediment is deposited annually in the Yangtze. Much of the sediment now accumulates behind the dam, and that's a major flux of sediments, nutrients, etc., that are no longer reaching the Pacific Ocean. So one of the other concerns in this area is that as this area gets hydrated and along these tributaries, there are increases of landslides and stuff like that as a result of the rising water. And in essence, these are all sort of what I talk about in terms of predictable surprises. We really should have known this was going to happen. In reality, the people built the bridge did. They again make a assessment based upon energy poverty, water poverty, and the ability to control transportation in the area. So these are controversial issues. I'm not pretending they're overly simple, but they are sort of predictable at any rate in terms of what's going to happen in these areas. So switching away from dams, we're going to talk about going back to the idea of what's happened in like Olentangy in Ohio, in Columbus rather, is basically looking at channel patterns and how, and much of the work in environmental science, rather than using dams and civil environment engineering as well, rather than building more dams, is actually looking at natural analogs for river channel patterns and floodplains, and actually designing optimal or engineering optimal floodplains to minimize it. So one of the things I want to bring up here is just the different types of end members of channel patterns. I already alluded to a braided river, but a braided river is an area, where usually in nature there's a deep longitudinal profile, and as a result you see abundance of coarse bed load material, the stuff that sort of rolls along the bottom of the river channel. And as a result, this creates kind of a chaotic pattern of braided flow through here. While that can be really fun, as behaves as rapids to take a kayak down or something like that, one of the net benefits is that it actually causes the water to move around, dissipates a lot of the energy in here, and it actually has a net result of slowing the water down as the discharge comes out of that area. So broadly speaking, in nature, these tend to be in montane areas with broad flood plains and broad flow channels, but the braiding actually has a net result of causing the water to slow, and as a result there can be flash floods, but they often can be mitigated by the water being spread out over a large area, basically expanding that flux equation by widening the channel. So there's been like we showed in the example in the Olentangy and Columbus, there's a result of trying to broaden the channel and make a more chaotic braided flow in that sort of equestrian or the aquatic system in the wetlands, slow it down, have some of the water penetrate into the ground. And that's a key aspect of these systems, that when you slow the water down, more of it can actually penetrate into the subsurface, minimizing the amount of water that has to discharge through the river, which over time helps mitigate flooding events. The other pattern, that's the other end member, I should say, is sort of a meandering pattern. And these are often, you see these in coastal plains like Mississippi, for example, as a very common number of these. And usually these are the opposite. They're in very flat-lying areas where the water is just slowly making its way along a gradient. And what happens is when you have major, we introduce the river channel, sort of meanders. That's why it's called the meandering channel. The floodplain can be relatively wide. What happens is there's no clear gradient to drive the water in a given direction. So what happens is over time, the water just sort of meanders around. When this water comes here, it erodes sediments along these banks and erodes it over further, sort of having the floodplain migrate out in this direction. And as a result, there's often sediment deposition along the backside of this where there's not a lot of erosion occurring. So the river banks can actually migrate over time in here, meander further over here over time, here migrate out, here erode. And as a result, these meandering rivers, during often major flood events, when water comes rushing down through here, can actually cut this channel off and make what's called an oxbow lake. This is what OBL means here. So I'll show you a picture of this here. This is in 2006. This is in Galveston area, and you can see that there's a meander that sort of slowly built up over time. This is back to 1944, and presently, after that flood came out here, the river basically breached the channel and led to what's called an oxbow lake back in this area. But now the river just sort of straightens itself out again. So over time, given this is a flat-lying plain, relatively slow-moving water in non-flood times, the river will start to meander again, and that same process will occur again and again and again. Eventually, that banks will flood the banks, and actually the river channel will quickly erode the oxbow lake, the sort of turn of the oxbow lake, and straighten itself out. So these patterns tend to repeat themselves over and over and over again. So this meander is just another way to actually slow down water flow. Obviously it's a natural system, but in terms of engineering them for flood mitigation, it's another example of a way to slow down water flow by creating a meandering pattern. But of course, there's risk they can sort of breach the banks and create an oxbow lake. So now what we're going to talk about specifically is the terminology around flooding. The key aspect of river flooding comes back to the idea, I think we all sort of implicitly know this, of overbank flow. When the banks, no matter how wide the floodplain is, no matter what the river channel looks like, floods that impact human lives and impact infrastructure and things like that typically can come back to the occurrence of when the water actually reaches a critical height that overflows the banks and leads to major flooding events. And basically, the channel discharge at the point where water overflows the channel, breaches the river channel, is the flood discharge. And this is used as a magnitude of the flood event. So the key terminology I want to introduce to you here in terms of river flooding comes back to the stage. If you're listening to the news during a major storm event, you'll often hear the river stage is at X. And really, all it is a fancy word for saying how high is the river. So there are fixed locations. The USGS, or the United States Geological Survey, they have a variety of flood monitoring systems around the country, even back in creeks, streams, rivers, you name it. They have flood gauges there, and what they do is they continuously monitor the height of the river in a given area. That height, they know the river channel, so that height allows them to actually calculate the discharge and the velocity in a given area. And that allows them to basically make downstream predictions as to when that water is going to reach critical heights downstream. They've had a lot of experience doing this, monitoring different size storm events and how much that increases height in X, Y, and Z areas. As a result, the flood stage tells you when the surface area of a given area has reached a height where damage to human property can occur locally, or more importantly, projected to occur downstream. So the key aspect, I should have said this earlier, when we're thinking about flooding, is the fact that we have to, during flood events, we're inherently increasing the Q by more water coming into the system, or the discharge by more water coming into the system, which can cause the height to increase. But as a result, you typically, with a constant size river channel given area, increasing the amount of water coming in, increasing Q means you're increasing the velocity, which is a component of this as well. So there's sort of two end members of flooding. One is called flash floods, the other is downstream floods. I'm going to take you through each of those here in a few moments, but both of these can have pretty different behaviors. Probably inherently you get the sense that flash floods come through really rapidly, and that's the case. Downstream floods, on the other hand, can occur over really long periods of time. So typically speaking, flash floods of rivers or creeks and streams often occurs in sort of V-shaped narrow channels. So obviously, if you're in an area like the Appalachians to the east of here, where there's more mountainous areas and narrow creeks and hollers, if you will, there's often potential for more flash flooding in those areas where the channel is relatively small. Normally, the water keeps the river channels contained. Major flood events, the water sort of episodically increases, can cause flooding of houses and infrastructure, and then blows through. Alternatively, downstream floods are usually in much more flat-lying areas. They're where the massive amount of water that builds up in the entire drainage basin. It eclipses the carrying capacity of the river downstream, and often these can be very expansive. There are plenty of examples in the last few years, even the Mississippi River flooding over the course of miles and miles around the river because the water will dramatically exceed the banks, and these typically occur in relatively flat lying areas, not necessarily where there's a meander, but where there's relatively you know slow, broad alluvial floodplain patterns. So these can both be over massive areas, but they also can exist for really long periods of time because there's no elevation to drive the water away rapidly. So how's this done? By and large, I mentioned the monitoring of the river stages by the USGS, and these are all continuously monitored over time. It's a pretty simple system. There's a pipe in the bottom of the river channel, measures the volume of water and pressure in there, and actually provides an electronic signal now in almost all cases back to an integrated drainage basin that lets people have field measurements of what's happening. So what'll happen here with stages, there'll be a major rain event. The stage height, the height of the water will increase. Recorded by the stream gauges, you'll see it peak and then basically drop off over time. Obviously, I think hopefully it's relatively sort of same concept, but when the stage height increases, again, that's more water coming into the system. That means the discharge is going to increase, and you'll see the discharge, the Q, basically show a pretty similar pattern, although on a different vertical scale than stage height. And then over time, what happens here, as you can sort of see, is that as the stage increases, this means more water is moving through there. So stage and discharge tend to be sort of positively correlated with each other. Moving, into practice, what's typically done, by looking at these stream gauges in terms of continuously monitoring, in all areas, both in areas prone to flash flooding and in areas prone to downstream flooding, is they're typically used to assess risk before flood events. And the main way we do this in the United States is basically looking at a magnet is one of two ways. One is by looking at the discharge events historically. So basically, the y-axis here is the recurrence over how often we see this occurring, and then the x-axis is how often we see this occurring. The y-axis is how much water comes through. So people monitor at each of these flood gauges how much water has come through. You'll plot a sort of a bar graph or a distribution of how many times we've seen 100 or 200 or 500 cubic meters per second, and then basically that's plotted versus on how often we see that occurring. So if there's in the last 100 years there's 5 events with 450 cubic meters per second, that would give us a recurrence interval, and you call that a 20-year flood. You'll hear that, or a 100-year flood. And basically that's the magnitude is sort of correlated to the discharge, and then the recurrence interval is calculated by the number of times a given type of flood occurs plus 1 divided by its magnitude, and that sort of give you a recurrence interval. If you were going to say, hey, we have a flood here that produces 750 cubic meters per second, how many, the way you would do that is, so we have one of those divided by the magnitude. That's how often that's going to recur. And that basically is the two ways it's done. I put the article about this from the New York Times on the Carmen site, but one of the things that's been really controversial in sort of civil environmental engineering as well as environmental science around and geologic hazard risk assessment around rivers is the fact that the way we've done this in the past, particularly in light of climate change, in light of changing precipitation patterns, is that we're actually observing that these estimates are now, the recurrence intervals are actually been severely overestimated. So people build houses, property, et cetera, in 100-year floodplains, expecting there to be an event once in 100 years that comes through here. And now in many cases, we're recognizing there are flood events that occur more frequently than that. And there's a major, read that article, I'll have more detail about that. There's a major effort to say, wait a second, we built this in a time where we're expecting the population to be XYZ. We expected risks for flooding to be, some other variable, and then we expect the climate to be this. All these things are changing, and as a result, most people now suggest that the recurrence intervals are dramatically overestimated, where flooding events in a given area are going to be much more frequent. And that's, independent of independent of what problem you attribute the flooding to, or realizing it's all of them. Most people now recognize that, in my lifetime, and certainly in yours, we've had several, 100-year events in a few decades, which obviously tells you these are probably wrong. So, once these, once a number of events occurs, recurrence interval versus discharge, this is like to say this is a 20-year event or a 100-year event. What does this mean? I guess in essence, nothing, right? I mean, mainly the reason people even talk about this is trying to predict risk. It's more about creating, insurance estimates for how likely it is to do, to a flood will occur. So they have an estimate of how likely they're going to have a problem to pay out. If you're building a home, obviously this is, or placing a business, or buying a farm, knowing the risks for that type of events are obviously really important, because it gives you an estimate of how much risk there's going to be in building those areas. But in terms of thinking about that, I encourage you to read the article I mentioned. So specifically jumping into the flash flood, this goes back to those to these gauge height things, stage or discharge versus time. So that's what we're looking at here. And this is basically the stage, the height in feet here, because this is in Arkansas. It's a state gauge, not a USGS gauge. And this basically gives you an idea. This is the measured gauge height here in the height of the water in blue. And a flash flood event will sort of be nothing, major rain event. And you'll see that the gauge height will rapidly increase. In this case, increase from about 3 to 24 feet in, what is that? Maybe a sixth of a day, so 3 to 4 hours. Okay. And you'll notice that flash flood will dissipate out relatively quickly. These, again, areas of narrow channels, typically with high topography, where the water can quickly get into the river channel and quickly dissipate through there. It doesn't mean that flash flooding can't be as horrific in terms of damage. And as an example, this was following a 100-year flood near a campground, where just as recently as 2010, this wiped out an incredible amount of property, and actually was responsible for killing about 20 people in this major flash flood event. These are, again, particularly common in the Appalachians and the more mountainous areas of southeastern Ohio, eastern Ohio in general, and over into Pennsylvania. Flash floods, where this topography and narrow river channels can be really common and actually quite devastating. And then, for perspective here, this campground actually experienced 2 feet of increase in water. So, in 15 minutes. That gives you a perspective of how rapidly this water's moving up. And, I don't recommend ever doing this, but if you're driving through a foot of water, think about what it would like to drive through a foot of water versus 3 feet of water. There's a very big difference in terms of how much risk there is to someone trying to get through those areas. Similarly, flash floods. This is from September 2015 near Hilldale, Utah. Relatively small, short creek here is its name, and it went to basically it was a dry riverbed. Okay, so basically no water in there at all. It's sort of a river wash. You can drive through it, walk through it. Some people even try to grow crops in there. And then within a matter of a few hours, they went from nothing to up to here to 4 feet, some oscillation, and capped at 6 feet in this river channel. You can imagine for folks trying to walk through there, drive through there, or just living near there, how devastating that was. Again, this is a 100-year flood, and sort of instantly almost killed 16 people. Moving on to, just for a little background here, that's an area where there was a sudden 2.5 inches of rain in 3 to 4 hours. Moving on to areas like the northeastern United States, around eastern Ohio and Pennsylvania, often these flash flood events could be as a response to major thunderstorms, or more often have been associated with things like the remnants of tropical storms migrating up the coast, putting huge amounts of rain, just like we talked about in Houston. I know things like Hurricane Agnes and Sandy. It's just some examples. Those are 1970s and about 2010-ish. Both are examples of areas where flash floods came into the area and rapidly caused major increases in stage height in our neck of the woods. So these can be devastating and can kill an awful lot of people. The other end member here, opposite of the flash floods, the downstream floods, and this gives you an example. This right here is the river channel for the Red River. Okay, you'll see a few things in here. You notice there's actually a lot of ice mass built up in the river, but this, for perspective, is the difference between a flash flood, which rapidly increases the water in the flood in the narrow valleys, versus the downstream floods. Where I noticed when the banks of the Red River were overflowed, notice the flooding extends out as far as you can see in every and all directions. Okay, this can be over the course of 20, 40, miles in some cases. The Red River, for some background, is somewhat unusual in that it flows north into Lake Winnipeg. Most rivers coincidentally flow south in North America, but that's neither here nor there, I suppose. The main reason to bring that up is that as a result of flowing north, as the river discharge progresses to the north, particularly in the spring during the snowmelt, there often can be ice dams, and that can cause the river to sort of back up, causes the stage height to increase, and actually can cause overland flow in the river backstream or further upstream. And again, the other aspect of this meandering, broad, usually alluvial filled river channel is that once you reach the banks, or once you breach the banks, you're often in extremely flat lying areas. So few places to shelter, and that flood can expand great distances, basically just depending on how much water is either introduced into the system or is rejected from flowing out of the system, both of which were relevant in the Red River. So commonly in low-lying areas, flat low-lying areas, typically with alluvial sort of meandering river plains, these can lead to extremely wide floodplain deposits in an area, and more importantly, these are common around times of the season where you have snow melt. So for example, every year it seems the upper Midwest recently, you accumulate snow, you get a warm snap, you get massive amounts of, typically with precipitation like a rain event, and you'll see major flooding events as snow melts on top of the flooding. Other examples, of course, are tied to major tropical storms, which can cause the river flow. The key thing here is once the banks are breached, this flat areas is really no place to go. Here it was exacerbated by the fact, again, that it was cold. There was ice dams further upstream. Water wasn't able to easily penetrate into the ground because of the fact the ground was frozen. As a result, it really was quite expansive. So as opposed to that, flash flood, which comes and goes in hours, not that it's any less devastating or deadly. This gives you perspective on the preceding gauge height here. In March 25th of 2009 was around 30 feet. And notice it actually only went up to about 41 feet. So that's only 8 feet increase in height. That's a pretty massive amount. But notice that led to flood conditions that actually lasted into April 4th and 5th, which is almost getting towards 2 weeks of a flood event. So these can be extremely large area, quite devastating, but most importantly can last really long periods of time because there's not really a place for the water to go, particularly when the ground's frozen. It's quite difficult in flat-lying areas for the water to be sort of moved away. So different types of hazards related to each one of them. Often in flash flood events, it's rapidly flowing debris that causes a lot of the death. And downstream, it's a long-term devastation of land and the fact that people are often left, suffering in flood areas for long periods of time. So this gives you perspective on the 2009 flood in Red River. Obviously, most people had to migrate to stadiums. This is in Manitoba. It was the second worst recorded since 1826. It caused major changes in sort of the engineering of the river channels in the area, where people decided to raise the dikes and walls along the river, trying to mandate that the stage height would have to be much higher to actually cause flooding. Here in Fargo, the people actually were just trying to immediately sort of put dikes along the river to hold back the river waters, bags of sand, things like that. But again, the river rose from an average of 22 feet, 33 feet right before this to 40, and there really was no way to hold it back in that area. So in all cases, when these river floods, I think we kind of know this implicitly, there can be a great amount of devastation. but it's very different to recognize what you're in for. A major flood event that's rapid, where something like a debris flow, branches and cars and things like that flowing down a river really rapidly can cause immediate damage. Where going upland and waiting a few hours can actually often mitigate the process, but then you can kind of go back to normal, except for the property damage. Here in downstream river floods, a common example here is that you have a lot of people sort of getting together in small areas. Um, Often the water sources for drinking water again are contaminated by debris, by chemicals, by turbidity or too much sediments in the water. And in many cases, the amount of damage and deaths to human life, or the amount of health problems and deaths to humans is nothing compared to what's relevant to livestock. But also, it's quite difficult to quantify, in the sense that most of the issues are things like dysentery and infectious diseases that come along afterwards, sort of waterborne diseases, because of an absence of good water access and people living in congested areas. Could you imagine, not to give you a terrible thought, could you imagine everyone having to move into a stadium like this now in light of COVID, what the implications could be? Well, some of those issues with flu season, things like that, are a problem that can cause major issues related to flooding. So for there, I'm going to end for today. We'll pick up next class with the urbanization flooding. Again, great job on exam 2. Keep it up. We're more than halfway there, and hopefully everyone keeps doing just as well. I'm gonna cut off there and start with urbanization flooding on Wednesday. Thank you.